Well, good afternoon, everybody. It is now 13:30. We've still got people rolling in, and the numbers are fairly rapidly going up. We're over 120 already. I'm going to slowly get us into starting the conference, recognising that people are still arriving. Kate, do you want to move us on to the slides, please? So what's on the screen at the moment is the program for today, and it's a really interesting program, or interesting from my perspective anyway. We're going to be talking about electrification clearances, and we are specifically interested today in how we manage the costs that delivering electrification clearances bring to electrification projects, and clearly that's about bridges. We're having this conference on a day when some further electrification in Scotland has been announced. East Kilbride to Barhead has been announced as going ahead, which is really good news. And I'm sure we all want to see much more of that occurring, particularly with decarbonisation coming up. So, without further ado, can I welcome very warmly everyone to this conference organised by the PWI. Cost-effective minimum clearance electrification is the subject. We have three tremendous speakers. We have Richard Stainton, David Johnson, and Andrew McNaughton, who will give us their views on some technical issues and on some wider issues of how we should perform to achieve the best results. I'm Peter Dearman. I'm the Deputy President of the Permanent Way Institution, and it's my pleasure to be chairing this conference this afternoon. The PWI has moved into offering meaningful membership to electrification engineers over the past few years, and we have a growing population of electrification people in the organisation, in the institution as members already. Membership of the institution is really a good thing for electrification people. It offers a communication method with the journal published monthly, with many facilities to be accessed through the PWI website. And it also now offers the opportunity for formal registration and some really quite good training courses now. Particularly, I would highlight the electrification diploma, which is available to anyone to attend the diploma course, and has a really useful value in taking forward people's understanding of the subject matter, but for the individual also helps with registration qualifications. If you're interested in any of that, you can find out about it on the website. From the training perspective and the education perspective, we have with us today Dr. Brian Counter, who would be happy to take a call or an email from you at any time to inquire into that. We have, over the past few years, had electrification conferences annually, and COVID has got in the way for the past 2 years. We should have been, had COVID not occurred, holding this conference well over a year ago, but we couldn't. We tried to organise it for Glasgow in the run-up to COP this year, but unfortunately COVID got in the way again. We will be running the full conference in April next year. But today we are running this virtual conference. We will cover some methods available, which if we can, as an industry, apply them effectively, will reduce the burden of cost on electrification for civil engineering interventions. CP5 saw a programme of works which was successful in delivering electrification on Great Western, but cannot be seen as a success in our industry's ability to deliver cost-effectively affordable electrification schemes. We have to correct that, and part of that is avoiding unnecessary civil intervention works. With the prospect of a rolling programme of electrification offered by decarbonisation measures, we have to get electric traction costs under control. And part of that is not doing unnecessary things to the infrastructure to make electrification necessary. What we're talking about this afternoon will, in my opinion, be a large ingredient of that cost avoidance. So, remember, please, the full annual conference will talk about other subjects beyond bridges and avoiding civil reconstruction next April in Glasgow. Please think about whether you want to come along and join us in Glasgow for that meeting. At that point, let's pick up and move on now to hear from Andrew Haynes, our keynote speaker. Andrew wasn't able to join us today, but very kindly gave up some of his time and recorded his keynote address to us. And I'm going to, without further ado, allow Andrew to do his talk. I'm sure he doesn't need much introduction to anyone on this call. Kate.
Hello everyone, I'm Andrew Haynes and I'm the Chief Executive of Network Rail. I'd like to thank the Permanent Way Institution and its Deputy President, the electrification legend that is Peter Damon, for inviting me to contribute to this conference. I'm genuinely sorry I can't be with you in person, but I'm really pleased to have at least had the chance to speak to you virtually. I mean that because decarbonisation is one of our industry's biggest opportunities and one of our biggest challenges. We get our approach right and we secure the future of our country's railways as the UK's greenest form of mass transit for generations to come. We get it wrong and we lose ground to our competitors and throw away one of the railway's major selling points, its sustainability. Now, I was pleased to see the government support proposals for, and I quote, ambitious, sustainable and cost-effective programme of electrification in its transport decarbonisation plan. But it would be a massive mistake to think that we now have a blank check to decarbonise the remaining 60% or so of our network. The ball is now firmly in our court to demonstrate to government that the railway is capable of delivering value for money for every pound spent on decarbonisation. Demonstrate that we have learned from the lessons of the past. It would be stupid to underestimate the damage that has been done by the horrendous cost and schedule overruns on Great Western electrification, to name one project. Demonstrate that we can be trusted to deliver on schemes efficiently and at reduced cost. That means zeroing in on issues like achieving minimum clearances, which I know is one of your topics for discussion today. Dismantling and rebuilding bridges is self-evidently both prohibitively expensive and massively disruptive. And we've seen some good progress in recent years through new methods such as Elevarch and voltage control clearances. But we have further to go. Critical to future electrification will be a relentless wave of innovation and collaboration to make it more affordable. That demands a different approach from the one Network Rail has sometimes relied on in the past. It demands a different sort of contractual relationship and a different sort of appetite from the supply chain to offer up innovation. We have some reasons for hope. Our colleagues in Scotland have embarked on this pioneering spirit and are making brilliant progress electrifying their network. They've set a target of spending less than £2 million per electrified kilometre. That's all in and inclusive of all civils interventions. And they have a clear deliverable pathway to achieving that. Now, considering where we started from a decade ago, this would be a wonderful achievement. However, when you bear in mind the pressure on the public finances and what we know to be benchmarks internationally, we have to challenge ourselves to push even further on every front. The vexed issue of parapet bridge heights alone could save us many hundreds of millions of pounds if, as an industry, we can address some standards which frankly have not been sufficiently challenged in the past. But clearly, fine-tuning our standards alone isn't going to be enough to make up the ground. We have to innovate and be open to doing things completely differently, as I've already said. Take the use of voltage-controlled clearances, which provides the opportunity to electrify without rebuilding bridges, as was demonstrated in Cardiff. Can you imagine a world where we can electrify entire routes without having to dismantle a single bridge? And in that respect, it would be wrong for me not to mention some of the developments we've seen in power in the railway too. In CP5, working with National Grid, we collectively managed to reduce the cost of connecting the railway to the electricity grid to something like £100 per kilowatt, and we're looking to go further still. Static frequency converters have helped our eastern region save hundreds of millions of pounds. And on Wells and Western, we've demonstrated that rationalised distribution can significantly reduce the cost and size of modern substations. I make no apology for saying that devolution is at the heart of our approach, giving regions freedom to innovate while strengthening our ability to benchmark and bring everyone up to the standards of the very best. I remain frankly bemused by those who see devolution as a cost risk when we look at what has happened to electrification costs under a centralised system and how we are already beginning to turn that around through devolved accountability. So with COP26 looming, the government's approach to hitting its decarbonisation targets is going to be more scrutinised than ever before. It's our responsibility to make sure that rail is seen as having learned from the mistakes of the past and is central to achieving the government's target to hit net zero emissions by 2050 at the very latest, and of course earlier in Scotland. We are moving, albeit slowly, in the right direction, but there is so much more to be done. Successfully decarbonising the railway will require all of our collective expertise and all of our capacity for innovation. I genuinely believe that working together through events like today and the learning that should come from them helps us show we can be trusted to deliver in an affordable way, project by project, milestone by milestone, carbon saving by carbon saving. Thank you for taking the time to listen to me. Enjoy the rest of your conference, and I really look forward to celebrating the fruits of our collective labours.
Well, thanks to Andrew for that. Messages were very clear in there, I think, and it's good to hear that Andrew is giving his support to us moving these issues forward. Now we're about to go into the presentations by those live on the conference, and I want to say a few words about how we manage the Q&A sessions in this part of the conference. There will be Q&A at the end of each of the individual presentations. As attendees at the conference, you are very welcome to type your questions in to the questions area on the website. If you type your name, please, and the person to whom you wish to address your question, which I guess will normally be the presenter speaking, but you're free to push that in any direction you wish. I will, during the Q&A sessions, pass those questions on to the presenters, so as attendees we don't end up with a cacophony of voices from the now 230 plus people listening in today. The conference is being recorded, and you'll be able to look at that on the website after the event. So now I'm going to move on and introduce Richard Stainton. Many of you will know Richard. He has been around for a fair time now. Richard started his railway experience with some time in Derby, where he was involved in testing the Eurostar rolling stock. That was in 1993. By 1995, Richard had joined Railtrack, as it was then. That date, 1993, marked a turning point in passenger numbers on the railway. Growth has been a feature of passenger numbers every year since, COVID notwithstanding. And that growth has continued across all of that time. And although Richard's never actually claimed that it's his personal responsibility that occurred, he has mentioned it to me more than once. Richard initially did some time in Anglia with the E&P team, where he became engaged in electrification and developed a passion for electrification work. That passion remains undiminished, and anyone who's spoken to Richard will know how strongly he holds his opinions. I first met Richard on the West Coast Route Modernisation programme, where he helped to develop the UK industry approach to 25/0, 25/80 feeding, and has been a great advocate of that feeding system ever since. Now working for Network Rail HQ, where he's technical engineering expert, Richard has always been and remains an advocate of engineering intellectual reasoning. He's never reluctant to challenge accepted norms, and he's pioneered and championed developments in technology and practice in many areas. Today, we're going to hear from Richard about the fundamental work he's successfully completed on electrical clearances at bridges. Richard, over to you.
Okay, well, thank you very much, Peter. I don't know what to say for that introduction. It's very kind. Okay, hopefully everybody can hear me, and I'll press a button and see what happens. Okay, great, it works. So my presentation today is titled Mind the Gap, or really respect the gap, respecting the gap between bridge soffits and the railway, and how to avoid making those gaps any bigger when we electrify the route. It's trying to achieve Andrew's target of 0 bridge reconstructions when electrifying a section of line. As was said before, the electrification costs in control period 5 escalated for a number of reasons. We've put aside the reasons to one side for the time being. The cost of electrifying a route can be split broadly into thirds. 1/3 of the cost is associated with the overhead line equipment, the foundations, the masts, the wiring, and the commissioning of the system. Of that third, a small proportion is actually the material cost, the rest being plant and labour. Another third is regards signalling and other immunisation costs, along with devegetation, traction power connections, and compensation to operators, etc. And so that leaves 1/3 with regards to civils works, so lowering the track in tunnels, cutting back station canopies, and work at bridges. And as I said earlier, there's two main types of civil works at bridges, either bridge reconstruction or increasing the height of the bridge parapet. Over the last few years, the standard practice is to make the parapet height 1.8 meters tall. Very simple requirement, but not so simple to implement in practice. A number of solutions that you can see on the left of the picture, and whether it's encasing historic railings in a stainless steel panel, or whether matching the existing construction technique of the bridge is all add cost to electrification projects. When matching the construction techniques, we often trigger wind loading considerations, and we increase the static loading on the bridge itself. To meet the new requirements on wind loading, we often enter a wall that's wider than historic practice, and that means that we lose the standing surface area on the bridge itself. Acceptable in the picture in the middle of the screen, but it wasn't acceptable on the bridge on the left of the screen. And so to increase the parapet height and not overload the structure and not reduce the standing surface of pavement, it requires extensive civil works just to get those extra 30 centimetres of height on the parapet. And really all we're doing is tracing how long is a piece of string, and there's not a very efficient way to manage this risk. We've undertaken a very comprehensive risk assessment, looking at all the electrical shock instances that occurred at bridges over the last 18, 19 years. I can demonstrate that these measures that we've applied in CP5 are disproportionate to the risk and not very effective at avoiding electric shock. We've shared our findings with our key industry stakeholders, including RSSB and OR, and we've gained a deviation for the first bridge in the East Kilbride electrification project not to install a bridge parapet of 1.8 metres. However, we also recognise that one size will not fit all, and at certain high-risk structures we will need to take additional precautions. The findings to date suggest that applying a near horizontal screen, like you can see in the bottom of the picture that was used on Heathrow Express, offers a far more robust mitigation against electric shock than simply raising the wall. By deflecting an object away from live equipment and providing a earth path should a flashover occur away from members of the public, we end up with a far stronger mitigation. But that's one opportunity that we've developed with regards to bridges. The main cost in terms of bridge reconstruction is how we get the wires underneath the bridge. In the good old days, as people have reminded me many times, we followed the Blue Book, which was published by the Department of Transport. This had a hierarchy showing normal clearances, reduced clearances, and special reduced clearances. And for each of those levels in the hierarchy, we had a simple and well understood set of assumptions and design tolerances. However, when you explore it in more detail, there are a few abnormalities that occur. For example, if we break those same dimensions out and plot them on a chart, you can see the uplift, which is shown as the yellow area on the bar, or the columns rather, reduces as the soffit height of the bridge reduces. So as if by magic, the pantograph recognises that there's a low clearance bridge ahead and will reduce the contact force exerting on the contact wire. Now in CP5, a number of factors happened, including the fixed deadlines for projects for authorisation and the combination of the TSI, GLRT 1210, ASBOs, DBOs, etc. And projects were unwilling to jeopardise the authorisation of electrification and that start of service stage. This meant that clearances grew rather than reduced, and in many cases the clearances in control period 5 were almost up to 5 metres in terms of the soffit height. So just as when competition arises from hydrogen and battery trains to decarbonise the railway, electrification becomes unaffordable. As part of the efficient electrification programme, we've looked at these clearances and tolerances and examined every single one, applying, if you like, the marginal gain philosophy of British cycling to electrification. And we believe now that we have a robust engineered solution that can deliver clearances far lower than was done in the past and a soffit height of about 4250 as a minimum soffit height, while maintaining gauge clearance to W6A and compliance with all key railway standards. And the key railway standard is obviously GLRT 1210. This requires a electrical clearance that's been derived from BSEN 50124, or a reference system in terms of 270 millimeters, or a risk assessment. 5124 requires a electrical rating of 200 kV for basic insulation. 200 kV is not a new value. It's a value that's been used for the last 50, 60 years for testing and demonstrating insulation rating of overline insulators or switchgear, cables, transformers, etc. So it's a long-standing impulse value that's used for 25 kV electrification systems. And it's many orders of magnitude greater than a nominal voltage that you can see in the top bar on your screen. 5124 also provides categories for reinforced insulation, which is equivalent to double insulation, and functional insulation, which provides sufficient insulation for operation of electrical circuit, but not sufficient to prevent or protect against electric shock. 5124 also provides the maximum or minimum clearances required to withstand these impulses. So for basic insulation, a 200 kV impulse requires a physical clearance of 370 millimeters. This is worst case. It assumes worst case electrode design, but we'll be able to replicate these values in a high voltage laboratory. But when we apply voltage control clearances, we can achieve the same impulse level of 200 kV, same basic insulation rating, but with a much reduced physical clearance. So from testing, we can demonstrate we need 80 millimeters or less to get the same electrical performance. So no longer is the gap underneath the bridge the weak point electrically on the electrification system. Now that 200 kV is a transient trace, and you can see the 200 kV trace on this chart here as the orange line approaching 200 kV. It's a fast-fronted waveform trace. Transients occur on the electrification system for a number of reasons, where it's switching, or operation of a vacuum circuit breaker, or overline switch, or the VCB on the rolling stock, poor contact between the contact wire and the pantograph, or maybe even the high frequency switching on modern traction packages. Historically, British Rail carried out impulse testing to develop the electrical stress graded bridge arm back in the 70s. But this used a waveform derived from a British standard from the 1940s, which is much lower in magnitude and a slower fronted waveform compared to the modern day requirements, which is the blue waveform you can see on the screen in front of you. The advantage of applying a surge arrestor to a transient trace is it's able to absorb the energy, excess energy, and manage the overvoltage down to approximately 75 kV. So as you can see, the resultant waveform is shown in the green trace on the chart in front of you. The surge arrestors that we've used are applied either side of an overline structure with two surge arrestors on each electrical section. Those two surge arrestors provide a level of redundancy should one fail. The surge arrestor is connected via a jumper to the catenary of the overline system, and then connected to the earth connection of the overline structure by a jumper at the bottom of the surge arrestor. It's mounted on a 25 kV standard insulator and has an expulsion fuse at the bottom of the surge arrestor. So in an event that the surge arrestor is firmly overloaded, which seems very unlikely, then the expulsion fuse would operate and the earth connection would drop down, taking the surge arrestor out of circuit. The electrification system would still operate, but the protection offered by the surge arrestor would no longer be available until that surge arrestor was replaced. Surge arrestors are nothing new. They were developed over 100 years, almost 100 years ago, and widely used in the electrical supply industry and almost all modern electrical rolling stock. And it's not just Network Rail that's using surge arrestors in electrification projects. This is an example of the Danish railways, courtesy of Google Maps, and you can see that surge arrestors have been installed next to a low clearance bridge to mitigate the effect, to allow low clearances underneath that bridge. And here's an example of, in Tokyo, different electrification system now. I think we're 20 kV composed to the 25 kV system in Denmark. But you can see surge arrestors, similar concept applied to portal adjacent to the low clearance bridge, and supplementary insulation in this case also applied to the contact wire at the bridge itself. But where we are different to the other railways is that we've taken all the components that form the electrification system under the bridge and tested them as a system. Tests we've used in accordance with the standards you can see on the left, which require testing with both positive and negative impulse transients or waveforms. And it also requires those configurations are tested multiple times and withstand and provide a withstand and no flashovers before the configuration can be declared a success. Now we've enhanced the test requirements and standards by testing in wet conditions as well as dry conditions, and those wet conditions require a salt mist applied in the environmental chamber to take a real worst case environmental perspective on those clearances. And we further enhance those tests by applying a pollution to all insulated surfaces of the components that we're testing. The testing we've carried out is we're using University of Southampton, and you can see on the right hand side the voltage, the impulse generator and the transformers used to generate those waveforms. On the top you can see the environmental chamber used for testing the systems, and the connection between the two is the middle photograph at the top right. On the left you can see some of the bridge samples. So we've got the brick and the concrete samples at the top of the screen. And these were pre-soaked in what was known as a paddling pool for over the weekend before any testing commenced, so a minimum of 48 hours. And at the bottom there, you've got a steel plate representing a metallic bridge that's been coated in a insulated coating, a polyurethane insulated coating, and then had a pollution mix applied to the top of the coating. We then carried out a significant number of tests. This example of testing with a bridge arm, both with a steel plate on the left, concrete and brick sample on the right hand side. Now we weren't able always to get the orientation right, but fortunately electricity doesn't respect gravity, and the tests are equally valid even though they're carried out upside down. What these photographs do show though is just how close we're getting to the bridge and victim, what's termed the victim material of the in a test bed. Unfortunately, the photographs always look really boring unless we have a flashover, so I have selected photographs that do show a flashover, but rest assured that the path is only a few millimeters greater than these flashover photographs. And just to demonstrate that, on these photographs we're showing the top of the contact wire to a bridge structure, and as you can see on the right hand side, without a flashover, the photograph does look very boring. So similar to before, we've got top of the contact wire to steel, brick and concrete, and obviously the concrete sample has a secondary insulation in terms of contact wire cover applied to the test. We've also tested the bottom of the contact wire to the train roof to understand the minimum electrical clearance required. So on the left-hand side, you've got the minimum clearance, or a flat example of a flashover without a surge arrestor, and on the right-hand side with a surge arrestor connected, a dramatic reduction. Those gauge profiles we've used have been W6A, W10, and W12. And we then supplemented that by adding an aerial onto the top of one of the profiles to make sure we've got a worst case electrical stress visor on top of those profiles. And then obviously it lined up perfectly with the contact wire. We have also tested pantographs. So we've got the with RSSB, with the open horn pantograph design and a closed horn pantograph design. And further testing has been carried out in Scotland in service. So here we have a surge arrestor on the structure away from the bridge, and a insulated plate applied just directly above the bridge arm on the cantilever arrangement to allow it to swing in and out, should we have any problems with in-service trials. I'm pleased to say that the arrangement withstood the Glaswegian weather, and we were able to complete the test without a single flashover between the bridge arm and the plate. And then we've got Cardiff Intersection Bridge. So it was energised December 2019 and it's performing well to date. So we've tested around 20,000 different impulses. There's a selection of testing we've carried out there. To supplement those configurations, we've also added supplementary insulation in terms of the contact wire cover and the insulated coating applied to bridge victim plates. So we've got a wide range of options available to designers and projects to really minimise those electrical clearances. We've also tested pantographs both with a conducting horn and a non-conducting horn, following a success we've had with testing the pantograph horn from HS1 or the Javelin trains. We took a pantograph horn off an in-service train, subjected it to the impulse testing and found it was really promising. So that then prompted another avenue of development with Bretner Willis to develop a composite pantograph horn that can be retrospectively fitted to the HSP Mark II and the HSX pantograph heads. As you can see there, it's a simple bolt to be undone, the pantograph horn to be swapped over, and a new pantograph horn inserted and secured. We've carried out a number of tests and hope to get the trial commencing soon. Those tests have included very soon. Those tests have included a mechanical test and electrical test. We've applied over 1,000 newtons to the tip of the horn and measured the deflection at the key transition between the carbon carriers and the insulated horn. We've also carried out an abrasive wear test to compare the composite horn with the steel horn. And I'm pleased to say that the composite horn only lost 7% of its cross-sectional area, compared to a steel horn which lost 30% of the cross-sectional area in those abrasive tests, which operated on the same location of those horns for approximately 200 kilometers. Electrically, the horn does not flash over when a earth plate or earth rod is in contact with the tip of the pantograph horn. And normally when I talk about insulated pantograph horns, I get told they can't work on legacy infrastructure. Here's a photograph that proves it can. The North of London Eurostar trains operated with a composite pantograph horn or insulated pantograph horn, and these were operated on West Coast Main Line as part of trials, and on East Coast Main Line in service between Leeds, York, and King's Cross. The current collection test report from the mid-90s, I wasn't involved in this test, but shows that while the pantograph horn did not cause any issues, the uplift of the pantograph was a concern, and that probably brings us on to the next subject we've investigated. So working with Atkins, we've studied the uplift that are created by the passage of pantographs at bridge structures around the country. Using digital imaging cameras, we're able to record the uplift when the train passes, and resulting both at the bridge arm and the bridge approach span. We've monitored a variety of overline equipments, train speeds, and maintenance regimes. The resultant trace you get from each train passage is something similar to this, where you've got the time along the x-axis and the displacement caused by the pantograph passage, in this case 2 pantographs, on the y-axis. Summarising all that data together, we get a mean distribution, standard distribution, with a mean around 20 millimeters. 20 millimeters is, which is great because that aligns perfectly with our model results. And taking a mean plus 3 standard deviations allows us to gain 99.9% of the uplifts we measured in our sampling to include in our revised assumptions for the clearance calculations. However, we do recognise every so often we may get a rogue pantograph or rogue uplift, and therefore we have a opportunity of flashover. And so we have updated the Net Rail Standard of earthing and bonding to tell us to explain the requirements for earthing and bonding clearly, and we've also provided an e-learning website to communicate that visually, as you can see here, and access to the website is available to all on the link at the bottom of the screen. We've also looked at ice loading, because GRRT 1210 requires us to consider ice loading on the conductors when calculating electrical clearances. And normally we look at the clearance, the ice loading, as a round radial load, as a uniform distribution load on the conductor, as per the previous picture. But the reality of it, the ice in tunnels and structures forms as icicles, not as a nice round load, and doesn't respect the overline or the vehicle profile. So whenever we have icicles forming in structures, we have to send in icicle patrols to remove those icicles, and it seems irrational to assume that the loading would be anything other than that in the future. So we need to revert back to the methodology used in the old Blue Book and a number of railways around in Europe, and not to include ice loading in calculating electrical clearances. How does all that work? Well, if you take a pan profile that's typical from CP5, where you've got a W6A train gauge and a standard structure, a typical brick or masonry arch. On the right-hand side, you've got the black line showing the carbon carriers, and the grey line just below it showing the secondary horn. And the red lines and circles show the electrical clearance required to avoid flashover, according to CP5. But if we apply insulated pantograph horns, we take out the secondary horns out of the equation from an electrical perspective, and then apply site-specific pantograph sway, as David's going to describe later on, allows us to narrow the pantograph profile. Removing ice loading from the equation allows us to lower the contact wire height, as did if we use a revised figure for uplift. Applying voltage control clearances allows us to reduce the contact wire height down to the minimum of 4165, which is almost there, and now it's clear mechanically. But we are also able to apply for deviation against GRRT 1210 for the minimum contact wire height, as we've done in Cardiff and Scotland, to allow us to maintain basic insulation between the train roof and the contact wire, but lowering the wire height slightly below the established minimum, which in this case allows us to be clear for structure. But if you want to go further, there's also opportunities to install slab track. So applying this technique allows electrification projects to have simpler consents. We don't need to get permissions to change historic structures. Reduce track access. Reduce the impact on neighbours and train operators. And reduce cost to electrification schemes. So definitely putting passengers first. But in terms of electrification, we have a more pressing agenda. As Peter and Andrew have alluded to, we're not the only competition, the only option to decarbonise the railway. And for the electrification to be designed to be cost effective, we must apply these control measures to reduce the cost of electrification, and we need to apply them now. So that's my presentation. Thank you very much.
Richard, thank you for that. And I do like your new electrification poster at the end there, by the way. I'm trusting that you'll make that available so that everyone can put it on their wall. Yes. Richard, while we wait for some more questions to come in, we've got some already, but can I just take Chairman's prerogative and ask you one to kick off the discussion, if I might, please? Cardiff Intersection Bridge, what's its history since energisation? Have those arresters actually functioned? What do we know of that yet?
So the surge arrestor have functioned a number of times. The last time I heard it was over 25 operations according to the condition monitoring we installed in those surge arresters, which needs further study. But in terms of circuit breaker operations and flashovers, there's not been a single flashover since energisation almost 2 years ago.
That's pretty encouraging. And presumably you will be making those arresters legit, if you like, for routine installation in standards and other documentation?
Absolutely. So the surge arresters are currently product approved. UKMS OLE design range includes all the bracketry and design considerations so they can be fitted onto a wide range of overlying structures. In terms of the standard, we produced a guidance note that's going through the final drafting process at the moment, and that should be out before the end of this month. Will be out before the end of this month. And then that will be converted into a standard using the normal standard process. So that will be a couple of months after that, I suspect, when the next standard release occurs in December.
Okay, thank you very much for that. Let's go to some of the questions that have been put into the questions register. Andy Franklin has asked Richard, what in the analysis of the lower bridge soffits that you've put up on the screen in your histogram, Andy makes the point that track lifting tolerances seem to have disappeared. Is that correct? And if so, how does track get maintained without lifting, he asks.
I think we're looking to look at the track maintenance lift allowance. It isn't a requirement in any standard, and we need to go back to the way we maintained track previously, using the close tolerance allowances in either the Blue Book or currently in track 001 or the track construction standard, rather than rely on a lift allowance. We're not removing the lift allowance for the whole of the route, but just underneath the very tight bridges.
So it becomes a geographically confined restraint, in other words, Richard.
Absolutely. We have to manage the track underneath these structures as a managed track position. Okay,
thank you very much for that. Let's see, we've got another question here from Ali Muzabil from ACOM. He asked the question, will BSEN 5012 part 1 be changed to allow the parapet heights that you've spoken of here?
Yes, it will do. I am part of the working group going dubious pleasure of trying to get that redrafted. It's only taken us 6 years so far, but I'm pleased to say that the final draft following European consultation has now been sent to Senelec, and that will be voted on later on this year or early next year, and then will be translated to all the different languages of Senelec before it's published, hopefully spring or summer next year. That requires a different methodology, but involves a taut string line rather than a fixed dimension. But yes, but in the meantime, we have a risk assessment methodology that allows us to deviate from the requirement to follow 50122 as specified in GLRT 1210.
Thank you. Very good. We have a question now from Gary Bromley who's from Siemens. What impact do insulated horns have on permissible staggers?
Well, I don't think as much, Gary. I think we're only talking about for the contact wire to run on the insulated pantograph horn, we're talking about a stagger of or misband deviation of 600 millimeters, and the contact wire should not be there in the first place. It will only be in that area if it's an in-running or out-running contact wire, in which case there will also be a wire on top of the carbons in any case. So we'll maintain electrical continuity, and mechanically, if it's running an out-of-running wire on a non-insulated carbon, should not be an issue, or non-insulated conductor.
So in principle, Richard, I think the side is that it makes not a blind bit of difference to cross-contact arrangements.
Correct, yes.
Yeah. Okay.
That'd be a good way to summarise it, Peter. Yeah.
Thank you. Thank you. I've got a question from Graham Stubbings. I'll summarise Graham's question very briefly. That the air clearance under a bridge can be compromised by all sorts of things, pigeons, birds, nests, all sorts of debris getting under there. On Cardiff intersection, were any specific measures taken to protect against those risks?
Sure. So Cardiff intersection bridge, we've got clearances down to 40 millimeters. We have applied standard water mitigation measures in terms of making sure that any drainage from the bridge didn't fall out on top of the overhead line, and standard anti-bird roosting devices. But we also coated the underneath the bridge with an insulated polyurethane coating and applied a contact wire covers to the contact wire. So even if wildlife could squeeze in between those 40 millimeters between the contact wire and the bridge soffit, then we've got 2 sets of supplementary insulation to avoid the flashover event.
Okay, thank you. A question from Khalid Lagnatha, hope I've pronounced that name right. He's asking, with regards to the GLS paint, one frequent challenge by civils is the inspection of the bridge once the paint is up. Is there a business case for a removable GRP panel that is coated with GLS paint?
So first of all, it's not paint, it's a coating, as I've been reminded many times myself. So it is a very substantial polyurethane coating. And if you look on YouTube, you can see various examples of just how tough a polyurethane coating is. There's various examples of people coating a watermelon with a polyurethane coating and dropping off a fire station training tower and watching it bounce like a football rather than smashing smithereens. And there's lots of slow motion videos if you are so inclined to watch such videos. In terms of how we could look at whether we use a sheet, it's something that we are looking at. It's something that has been used for tramways in Europe, and yeah, we are certainly looking at it. But the challenge we have is making it fit the contours of our structures, which tend to be Victorian of nature and not very smooth or flat. So hence why we went with the coating. The coating is currently going through approval process to allow as a protective measure against corrosion, which would give us reduce some of those civil engineers' concerns with applying the coating to old structures.
Okay, thank you. I have a question from Matt Jackson. Will VCC become easier and quicker for designers to propose on projects seeking RAM approval, etc.?
So yes, I think that's probably a question about the existing standards on 27715 module 4, which requires, if we go into a reduced clearances, it needs RAM approval and I think it's approval of the professional head of contact systems or the national technical head. And yes, with the document we've updated will change those requirements so that we have a consistent approach to applying VCC in future.
Okay, thank you. You're getting lots of questions, Richard. You're a popular man this afternoon. And I guess what we will do is round up the ones that I don't get to put to Richard here, and we'll see if we can get some written replies onto the website. But just keep going with the ones that I'm picking up here. An interesting one here from Rodri Jones. Can OLE system height be reduced further if rigid bar conductor is used? And his secondary question, is it sustainable, reasonable to keep applying for derogations to standards to manage these issues? Two quite separate questions there. First, which would deal with the technical first, I guess. Yeah. Sure.
So the minimum contact wire height we've arrived at depends on the track geometry, but essentially it's 75 millimeters above the top of the rolling stock. This is where we've got to. And obviously that would be defined on the rolling stock that's operated on the route. So given that the vast majority of routes we clear for W6A and the other standard gauge profiles, that then sets the minimum contact wire height or any large conductor height. We're not talking about a Paisley Canal solution where we restricted the operation of rolling stock underneath the live contact wire height and went further as we did in Thameslink. In terms of rigid contact wire bar, it might provide some benefits, especially if you look at how we apply head roll in the future to designs. But at the moment, we're focusing on the contact wire design. In terms of deviation from 1210, I understand the pain. I've applied for the deviations myself first, and we now have a example of both wire heights and parapets to follow. It has been challenged with RSSB and the regulator, but the current legislation framework requires those deviations to be site specific, although we may have opportunities to batch some of those deviations in the future. GLRT 1210 is being updated at the moment, and hopefully in the future editions will remove the need for site-specific deviations.
Okay, Richard, thank you. And I'm just going to do one last question before we draw this to a close. This is from Andy McIntosh, and he's following up the question on track maintenance lift allowances. He's asking, we've always had these hidden clearances and tolerances in the calculation. If we're going to remove all those hidden tolerances, what are we going to do about the need for tamping under a bridge should that occur? Because the constraint could bring about the imposition of TSRs with unmaintainable track.
Well, I think if we need to look at, if we're not able to maintain the track with a ballasted track with a managed track position, then we need to look at other options, especially slab track, rather than looking at immediately jumping to rebuilding the bridge.
Okay, very succinct.
Rebuilding the bridges are the most expensive option we can get to.
It is. You're right, Richard. And we obviously, as a fundamental point on this discussion, that's what we're wanting to try and find out. And Richard, I'm going to draw it to a close there, because in the schedule for this afternoon, we now have a break in place for everyone to get a cup of tea, whatever else it is that you choose to imbibe at this time of the afternoon. We'll all be back together. If I can ask you to start getting back onto the screens at 10:02, we will make a prompt start thereafter. Thank you very much, Richard. Thank you.
Thank you.
Just to remind everyone, we're 5 minutes away now from reconvening and starting the conference again. Okay, well, welcome back, everyone. Hopefully everyone has found time to have a cup of tea, a bit of a refresh. Before I carry on to introduce David, can I just say that we have 255 people apparently on the conference call now. That's brilliant. I note though that we've had questions, I think, almost exclusively from the male members of the group. We are an inclusive organisation in PWI. Would any ladies on the call who are harbouring a question, please don't hold back. Please put those questions into the questions box. Let's move on now. We're on to our next presenter. It's a real pleasure for me to welcome Dr. David Johnson, the Technical Director at D-Gauge, to talk to us this afternoon. I've known David for 20, 25 years, I guess. David joined BR in 1977 and he worked in track maintenance. He was part of the team developing stone blowing and laser guided tamping, and in track renewals where he led the team developing laser guided relaying and ballast cleaning, which ultimately has led to the norm of line speed reopening after track renewals. In 1989, David formed Laser Rail, developing the computerized track design software and ultimately clearance software, which has since become his specialism. ClearRoute remains widely used across the industry. Following Laser Rail, David completed his PhD in simulation of clearances between trains and the infrastructure, and applied the lessons learned to a completely new gauging concept, which became the foundation of D-Gauge. This system has implicit capability to analyse not just physical clearances, but also the interface between pantographs, OLE, and the infrastructure. Over this journey, David has developed a significant insight into pantograph gauging, which can minimise wasted space when electrifying the legacy infrastructure. David, over to you.
Okay, hopefully I can be seen and heard.
You can, David. I'm going to shut.
That's nice to know that the technology's worked for me, even though that's supposed to be my business. But thank you for that introduction, Peter. And also I'd like to thank the PWI for the opportunity to presenting again at one of the conferences. I'm going to talk today about something called engineered electrical clearances, and what we're going to look at is a little bit more beyond what Richard's spoken about. Whereas Richard's spoken about the numbers that we need in terms of getting electrical clearances, what I want to do is to turn to the methodologies that we're going to use to do that. So without wasting any time, I'd like to go on to my first slide and make, I guess, a philosophical point to everyone about what we're trying to do. So my starting point really is a reminder of what engineering is all about. One of my heroes is a guy called Arthur Wellington, who was the chief engineer of one of the American railroads, who coined the phrase that any engineer can do for $1 what any fool can do for 2. And I think we have to remember this going forward, because we are all professional engineers. And I think sometimes we do get caught up in, shall we say, the big project mentality. And I think we've got to a position where we've become confused about what an electrification project actually is, where we're led to believe that increments in project scope are at marginal cost, for example, and that we're not really applying a true engineering ethos to the work we're doing. And the result of this is that in the past we've spent far more in electrification projects than was strictly necessary if electrification was actually the true aim of the project. Now today, as people have been pointing out, we have an electrification challenge ahead of us, not one to rebuild our railway. Certainly we have to do it well, but that doesn't mean that we have to do any more than electrify the railway if what we're trying to achieve is a zero carbon future. Just one point I wanted to make as well. We've spoken about the shall we say the different costs associated with doing rebuilding bridges, for example. Another standard way of electrifying is lowering track, and we've got an added dimension these days, of course, of platforms and accessibility. So a lot of the options that we've used in the past for electrifying and gaining the clearances aren't really there anymore. We do really have to start rethinking. And what I'd like to do today is to take you through a journey of how we can think about the engineering of electrical clearances. So what I'm really going to talk about, I think, affects mainly the masonry arch type bridges and the structures and tunnels. Clearly, we've got a huge problem ahead of us in terms of that a lot of the low-hanging fruit in electrifying the railway has already been picked. And what we're left with is 60% of the network where we have some of the most difficult structures to thread the wires through that we're going to imagine. And what I'm going to do is go through the sort of hierarchy of how we can look at getting the most out of our existing structures before we have to think about bringing the bulldozers in. So I'm going to talk a little bit about the traditional gauge, how we have done it. I want to move on to something that I'd like to refer to as the dynamic gauge, which is a slightly more sophisticated version of the traditional gauge. I then want to move on to absolute gauging, and then picking up the point that Andrew Haynes raised, which was about innovation, I want to talk a bit about probabilistic absolute gauging, which is, we'll call it new, a technique that's been developed that allows us to get even more out of our infrastructure, so that we understand the interface better before we actually start looking at how we improve it. We've talked a lot about soffit heights. Richard was mentioning about soffit heights. That's relatively simple gauging in the sense that we're only looking at the overall height of a vehicle and how that compares with, say, a flat deck bridge. It starts to get rather more complex, of course, when we're talking about pantograph clearances to an arch bridge. And what I'd like to say is that this is where we start to use what I call proper gauging, which is actually where we have to look at the train, the pantograph, the OLE, and the structure holistically and work out what our options are going to be. So I'd like to start off by looking at the traditional pantograph gauge. Now, everyone knows that gauging's easy. I'm sure there's an awful lot of people on this conference who've been involved in gauging in the past and would possibly challenge that statement. But you know, the world as a whole knows that gauging is easy. You make the hole bigger than the train, or the train smaller than the hole. It's as simple as that. And the measure of the hole size is the gauge. So let's have a look at what traditional gauging actually means from a pantograph perspective. Over the years, we've had tons of different gauges for different projects, but they all fundamentally have the same origins. They have a shape of a pantograph which is adjusted for the maximum possible sway of the pantograph as the vehicle's traveling along or around a curve, looking at the maximum uplift that could be achieved, sometimes looking at the maximum wind that might be applied, and you know, we do have some places in the UK where hurricanes are possible. We look at maximum tolerances allowance, and we look at 20th century clearances. So effectively, all we need to do with a gauge is to put our gauge profile over the top of the track, align it with the track, set the contact wire height, and the gauge line that comes out of it says you must not have your structure that comes within this space. Now, that's absolutely perfect, provided you've got that space. If it's a relatively big bridge, you know, the M62 traveling over the West Coast Main Line or something like that, not going to have a problem with using that sort of technology. But when we start to get down to very tight clearances or very tight structures, then we do find that we're seeing that we can't really get a pantograph through using the traditional methods. And I would say that the main reason for this is because a traditional gauge is very inefficient use of space. That, you know, for example, we don't have maximum sway everywhere. We don't have maximum uplift everywhere. We certainly don't have maximum wind everywhere. And I think although there are some versions of gauges that have got bits and pieces knocked out of them, the general principle is that the gauge, the traditional pantograph gauge, is pretty inefficient. So now I'd like to just move on to something else that we've looked at fairly recently. For those of you who aren't aware of this, there's a project recently been published by RSSB, T1196 research project looking at pantograph gauges and the development of new pantograph gauges that align with the findings of the work done under projects, for example, such as the pantograph sway project, that determine what the limit state movements were for pantographs. So what is a dynamic pantograph gauge? Before I go on to actually explain what it is, I just want you to look at the picture that we got on the right-hand side here, which is something we need to bear in mind going forward. It's a modern pantograph, and we've already seen pictures of those. Richard showing us the insulated horn, for example, on new ones. But the thing to note about that pantograph, as many of you will be aware, is that they have something called a floating head, and that is that the horn follows the profile, it follows the alignment of the train, but the head rolls depending on the stagger applied to it, the stagger seen by the pantograph. So that does mean that we've actually got yet another dimension on modern gauging that we didn't have some time ago under the traditional BR pantograph, which was relatively fixed. So we've actually got to consider other things now, as well as the simple factors that we had on the previous slide. So a dynamic pan gauge, the main difference between that and the static gauge that or the traditional gauge that I showed before, was that a dynamic gauge uses the sway of the particular vehicle, or more to the point of a series of vehicles, to say, instead of applying the maximum sway at any given point on the track, we apply a sway related to, for example, how much cant efficiency or how much cant excess there is and the speed of the vehicle. So in other words, what we're doing is, instead of putting the maximum sway on, we're moderating it depending on what the local site conditions are. And clearly you won't get as much pantograph sway on straight track as you would on curved track. We do apply the maximum head roll because we don't actually know where the stagger is going to be, other than perhaps left or right. And as you can see from the drawing at the bottom there, it's an asymmetric gauge that's resulted out of the stagger being set one way. But we do take it into account, although in a limited way. We do take into account maximum uplift. We don't necessarily take into account maximum wind. The dynamic pantograph gauges have been done for a number of different wind speeds. We do take into account maximum tolerances and allowances, and we take into account 20th century clearances. I use that expression because Richard, of course, has started to bring us into the 21st century with clearances now, and we probably need to think again about how these things interact to give us a better system. But dynamic pantograph gauges are all built around these limit state tolerance rules, and effectively what they do is they allow us to be a little bit more cunning, if you like, in terms of using a different gauge for a different position on the track, different points on the infrastructure. Still relatively inefficient, because we are limiting the number of parameters that we can vary according to what's reasonably manageable. Now remember, these things are generally, in the past we've had traditional gauges have been drawings, CAD drawings particularly. As we start to move towards dynamic pantograph gauges, we're starting to use computer programs to calculate what the swept envelope of the gauge is. And in the case of these dynamic pantograph gauges, RSSB has published a complete set of Excel spreadsheets where you put the numbers into it, for example, speed, cant, curve radius, etc., and it will work out the gauge for you to give you effectively the CAD gauge that you would have used before. So that's what I would call a dynamic gauge. So this is the dynamic sway, for example, and we can see from the top graph, we can see a traditional pantograph sway curve on straight track will be irrespective, on curved track will be irrespective of the cant efficiency, and on tangent track, again, irrespective of anything, it's just a dotted line with 200mm sway on it. What we've looked at with the dynamic sway is the red line, which shows that we have a certain amount of sway that increases as the cant efficiency increases. And along the bottom, you can see the effect of that on the actual pantograph itself. All of these numbers come directly out of Railway Group Standard GMRT 2173, which, as I said, relates to pantograph sway for any vehicle. In other words, any vehicle must comply with these curves. Therefore, in applying them to the infrastructure designed by this is compatible with any vehicle. And again, looking at head roll, this is the effect, as you can see it, that as the contact wire moves through stagger to the outside of the pantograph, then it causes the head on the other side of the pantograph to cock up in the air. And of course, we can see around the that area there where my mouse is following me rather slowly is actually the area where we need to apply additional clearances, and certainly around the horn area around here we can see that the head roll does require us to have more space. I'm now going to move on to absolute gauging, and some of you will be familiar with this because it's a process that's been used in for physically gauging vehicles for over 30 years now. It hasn't really got caught on in the pantograph area yet, various reasons behind that, but certainly it's something that we've been doing for a very long time once we realized that vehicles could have softer suspensions than the traditional gauging methods that we used in BR days actually allowed. Now, absolute gauging uses vehicle sway, and it would use these sway characteristics that are defined for specific vehicles in something called a RIS 2773 dynamics model. This is something that has to be submitted with every vehicle introduction that basically says for a given force acting on the vehicle on the track, this is the amount of sway it would see. It uses a specific pantograph model. In other words, we look at the different pantographs and say, how do they behave in relation to standards, in relation to the head rolls, in relation to uplifts, for example, the arrangements, the spring stiffness, all of those sort of things. We look at local uplift. We look at whether the particular steady arms that we're using have certain characteristics. We look at the wind speed, what that causes on uplift. And we look at the tolerances, allowances appropriate to the position, and look at appropriate clearances. The net result is what we can do is we can come up with a swept envelope for the pantograph that effectively is specific to a given vehicle at a specific location. Now, this type of introduction is often used on to introduce new rolling stock to legacy electrified route to avoid having to, shall we say, completely re-electrify because the route might be might not be built to the latest standards. For example, one that doesn't allow rolling head pantographs. An example of this was introducing the flirt trains to East Anglia, where one of the problems that we had was actually to try and demonstrate that the pantographs on the vehicle and the combination of roll of the vehicle actually meant that the vehicle could run underneath the electrical infrastructure, i.e. the steady arms, to make sure it didn't clash with them. And remember, of course, that the steady arms that we have on East Anglia, and indeed on a big part of our network, were not designed for floating head pantographs. They were designed for the traditional BR pantographs that didn't actually rotate at all. So what we did here was to look at various different electrification systems and determine where the problems were likely to be, and if possible, what the solutions to them might be. Here we have an example of where one particular situation, we realized that there was a clearance problem between the steady arm and a pantograph, which was solved by just using a 4 mm reduction in uplift. That itself allowed us to effectively introduce that vehicle past that point, knowing that it would fit. And again, another example here is again on the flirt project, where we can see that the physical clearance between pantograph and steady arm was increased from 13 mm to 15 mm by reducing the uplift again by 4 mm. So looking at the ways in which we can introduce solutions that don't involve replacing everything on the network. And of course, that's very similar to what we're talking about in terms of our avoidance of bridge reconstruction, which is in essence what we're trying to do going forward for our electrification. But nevertheless, it's another way of looking at gauging, and that is to say, if you can't get a traditional gauge to fit through, if you can't get a dynamic gauge to fit through, the next stage is look at the vehicles you've actually got running on the track and say, how can we get those through? And that is very different from saying, I want to future-proof my network to make sure that everything will fit through in the future. We're looking to electrify the railway for now. If we can electrify it for the future, that's great, but there could be a huge cost premium if we actually electrify the future, especially if we don't actually know what that future will be. So what I'd like to do now is to go on to the final part of my presentation, which is looking at something innovative but not necessarily new. Something that you may have heard about called probabilistic gauging, which I like to refer to as real life risk. And one of the interesting things about this is it starts to bring out philosophical questions, such as, for example, what is a clearance? You know, we say we want, for example, 270 millimeters clearance. Is that a number that exists, or is it something that's part of a statistical analysis that says we think our clearance is around about this plus or minus X? And I think you'll find that it's the latter. And what we're doing with probabilistic gauging, as I'm going to take you through in a minute, is look and say we're going to characterize the clearance numbers with a level of certainty to say how does my clearance relate to this particular location. Now, probabilistic gauging is it's not exactly new. It's based on something called uncertainty theory. And it's something that, if I take you back to 2007, something that we're working on at RSSB, looking at a risk-based approach to gauging. Now, probabilistic gauging is based on this uncertainty theory. It considers the likely aggregation of tolerances rather than tolerances, allowances, movements, etc., in the vehicle track system, and gives a probability of distribution of a clearance rather than this single number, which is usually related to the number you get if you say everything has gone wrong at the same time. Now, what you get out of a probabilistic assessment is actually a clearance probability distribution, and we set clearance based upon some level of quantified risks. The methodology actually allows us to explain why a lot of legacy rolling stock successfully runs when theoretically we say it shouldn't do. There's quite a bit of traffic that's old legacy rolling stock that's been running for donkey's years, that when you run it through clearance software and come up with the answers, it actually says you shouldn't be running this here. So it's a methodology that allows us to look at that. I'm trying to change this. Here we go. Right. Now, what we have here is an output from a probabilistic assessment on the left-hand side, which is a probability curve. But on the right-hand side, what you can also see is a vehicle wobbling around on the track, which says actually any one of these particular positions is where a vehicle might be going past a structure. And we see the amount of clearance varying. There's a little number up the top in the box. It's very small for you to see. I can just see it on my screen. Some of you may be able to see it if I move the arrow away. That's showing you how the clearance is varied depending upon the clearances that are put, the tolerances that are put into the model to make it actually test any different combination of tolerances and movements that it would have. So the inputs are applied statistically correctly rather than as limit state aggregation. And if you look in the bottom here, in bottom left-hand side, you'll see a cumulative distribution graph, which shows that in this particular case, our clearances vary between anything from 360 millimeters to 430 millimeters, depending on which way the tolerances are stacking up against each other. And what we say here, for example, is that if we were to use a 100% plus allowance, a traditional allowance, this particular structure would be deemed to have 315 millimeters clearance. If we said we were prepared to take 99.6% clearances, then that means we gain 35 millimeters as a result of my methodology not aggregating everything together. So we can see it makes an appreciable difference to the clearance that we actually calculate for a given set of inputs. Now, moving on to the next slide. Got it. Okay. On an example project, I think this is perhaps the first time we've ever looked at real clearances versus real trains, because obviously it's difficult to work out what the actual number is for a clearance. What we've done here is compared the probability distribution of a calculated pantograph passing a bridge versus measuring it in practice using high-speed cameras. This was done out on the old Dolby test track. We did it for a number of vehicles, including the Class 800 Intercity Express. We also did it for the Class 345 Crossrail vehicle. And what we showed was that we had an exceedingly good correlation between the probability distribution of clearances between a pantograph and an overbridge, theoretically, versus physically. So I'm rather proud of that test, that it demonstrated that the mathematics that go into the probabilistic clearance assessment are actually pretty robust, and for the first time ever have been demonstrated to pretty well match what we get in practice. So in summing up where we should be, I'd like to say a couple of things. Our options for stopping the bulldozers coming in are rather more today than they were previously. If you couldn't get a traditional gauge to fit in electrification schemes up to now, then it was time for the bulldozers to fill up with diesel and start getting ready to knock the bridge down. And I think somehow that we actually rather enjoyed knocking bridges down and rebuilding them. It was the thing to do. But if we look at going forwards to tomorrow and our challenge for the electrification of the future, we've got to consider that if the traditional gauge doesn't work, we've got to look at the dynamic gauge, we've got to look at absolute gauging, and we've got to look at probabilistic gauging. And we've actually tried all of these methods and used all of these methods in various places, but they're not mainstream yet, but they are engineering methods that engineers need to apply. And I think really what we've got to do is to make sure that we don't forget these in our portfolio of going forward. So we've got all of these new engineering tools. So what I'm doing is now making an appeal to you as a professional engineer to stand up to the project managers that might be intent on rebuilding the railway on the strength of an electrification case. We've proved time and time again that it's embarrassing the cost overruns that we have on our electrification projects. And I think one of the big things that we've fallen for in the past is things like, for example, if you're going to electrify the railway, you might as well open it up to W12 freight, for example. Well, interestingly, W12 freight is a classic example of a gauge that never actually materialized into traffic. It was something that was conjectured about 30 years ago. And indeed, the traffic that was postulated at the time never actually materialized, but that's actually the gauge we tend to think is what we should be doing for freight. But the issue is, of course, that it's only possible to get W12 freight if you electrify inefficiently. And what I'm trying to do is to encourage people to think about how we can electrify efficiently. We've got a once-in-a-lifetime opportunity to be part of the solution of the biggest crisis facing humanity by offering the low-hanging fruit of a decarbonised transport system by shifting to a wholly electrified railway. And I really think we have to be careful we don't blow it. And to paraphrase Arthur Wellington, any fool can electrify a railway, but only an engineer can just electrify a railway. So on that, I'd like to finish my presentation and hand back to Peter, and happy to answer any questions. Thank you.
Well, David, as one of the fools who has electrified some railways, I'm very pleased to hear your message. Really, that we can find ways of doing this. While we just have a look at the questions that have come in, can I just give you one to kick off the discussion, David, if I might, please? What other industries have used similar approaches, and what's the experience been there?
Well, it's very interesting because, of course, you know, we seem to be, I think railways are a special case. Somehow or another, we think we're more special than other industries, but it's used in the nuclear industry, it's used in the aerospace industry, and it's used in the automotive industry, because all of those industries have recognized that there is no such concept as absolute safety. And therefore, what they're looking at is to get the best engineered system using the minimal amount of conservatism necessary. And I think we can all look at those industries and say that we particularly if we start to look at, for example, aerospace, I don't believe we have any issues going on a plane and realizing that Rolls-Royce use these techniques day in, day out to engineer their engines. And indeed, it's not that long ago that the technical director, engineering director of Network Rail, who came from Rolls-Royce, wanted to introduce this technology into the industry, and really we just weren't ready for it. So we have had a problem, and as you've seen, 2007 was when we first started looking at it. I think we do have to ask ourselves why we haven't managed to do this yet. but we've now got the perfect opportunity to follow those industries. And I would also say that I think a lot of rolling stock manufacturers do use the techniques within the development of their rolling stock. It's just we don't use it in the systems engineering of, for example, the gauge.
Okay, David, thank you for that. There is a question in the questions that have come in so far, which kind of speaks to that a bit and enables us perhaps to return to that. Let me just bear with me a second while I turn it up. The question is from David Kennedy, and he's phrased it: how far away are we from probabilistic gauging being industry accepted? And I guess he means railway industry. I wonder if you have a view on that, David.
Yeah, I mean, it's interesting because I think it depends on looking at where we're going to put it in the industry. I, for example, was sitting on a safety review panel this morning where we're hoping to get the safety review panel case approved pretty well within the next couple of months to actually allow this to be used in terms of maintenance of permanent way. So at that particular point, we will have a framework that's been set out, that's gone through Network Rail's safety review panel process associated with physical clearances. Now, that I think should translate directly into electrification clearances. To be honest, the risks are slightly different. The risks in terms of physical clearances are the risk of a collision. The risks in terms of electrification are a flashover. So I don't believe that if we can get it through the safety review panel, certainly by within this year, I don't believe there's any problem at all for using it in electrification. I know that we have used it on a number of electrification projects to demonstrate a level of risk. And I think really what we can say is there's two stages to it. One is we can use it as a technique that has literally got the boxes ticked in to say, if you use this, is this number that comes out of it, you can use it. Alternatively, it's to inform the engineering judgment that we all make where we don't currently have numbers to stack up to give us the confidence in some of the decisions we need to make. And I think if we actually start to look at probabilistic gauging as primarily a tool that allows us to understand what is happening and give us a better picture, then I believe that we could use it tomorrow in terms of the decision making that we apply. But certainly in terms of the system review panel, the safety review panel, that is well advanced. I'm pleased to say at last.
Well, that's really good news. And I mean, I guess, you know, an observation from me is that the question is one that actually goes wider to the audience of this discussion, really, because it's the consensus view of the engineers in the industry which will adopt this, not the single point of contact. It's not you to adopt it, David, it's the industry.
Yes. Indeed, and I think one of the interesting things about it, Peter, is that what we're trying to do here is to develop it as a methodology that the industry can use, not, for example, as a D-gauge tool specifically. D-gauge has certainly been interested in developing it and taking it to this stage, but what we're actually publishing is the methodology that the industry would use and the way it should be used so that it's available for anyone to actually say, we can come up with a probabilistic methodology of achieving this or achieving that. It's pathfinding stuff, and it's not about IP. This is actually about saying we're part of a railway community, and my background is one of British Rail and, you know, being able to knock on the door of the person next door and ask the questions and get the answers without having to set a contract between us. So, you know, one of the things that would be great for me is to see this eventually get there. I think it would possibly be the pinnacle of my career.
Well, let's see if we can get you up to that summit at some point. That would be a good thing, wouldn't it? David, we've got a couple of questions here which are kind of linked. I'm going to give you them both before I invite you to answer. From Andy McIntosh, we get you talked about the uplift reduction of 4mm in Anglia. Andy asks, was that a change in assumptions or an actual uplift forced reduction on the pantograph? And Stuart Burrows asks that question in a slightly different way. He asks, were there uplift stops put into the pantograph to restrict that?
Yeah, I mean, that's an interesting question. I mean, the issue here is that what we were doing was looking at the maximum uplift or the uplift that was built into the gauge that was used to define the steady arms in the first place. So if we look at the steady arms and say that they were designed around, for example, 200mm uplift or 100mm uplift or whatever it was, then what we would say here is that using this new pantograph, then it would be 196 millimeters limit or 96 millimeters limit, and then we could look at it and say, are we getting near to 96 millimeters? Because the chances are we're not. So it's really a question of saying, if we use the same design parameters with a pantograph that's got a head roll on it against legacy infrastructure, it certainly won't fit. But if we actually look at it and say, how do we pull those limits back in terms of what the system was designed for, then instead of it being a 200 millimeter limit of uplift that the original infrastructure would accept, then what we're talking about is a 4 millimeter less in those particular cases. Some of them were more, but nevertheless, you can look at it and say, what uplift am I reasonably getting here? And Andy demonstrated some examples of uplift measuring, for example. I think we all know that in most cases, the uplift that we've designed into our systems is more than we generally get in practice. And therefore, what we're looking at is to say, we're not looking at the limit state of the original design, we're looking at a slightly less limit state to allow us to use these pantographs, and therefore we take the necessary precautions at that stage. If it needed anything to prevent uplift going any further than that uplift stops, then one would put them in. But I think in general, it's a question of looking at the situation, saying, this is the maximum uplift that we can tolerate at this point, are we going to get it?
And of course, that's consistent with maintaining the best dynamic performance in the overhead line without uplift stops. But
Indeed.
I think what it illustrates is that I guess you're worth $1, if I can put it that way, because the $2 we would have spent on someone who ignored that would have been money badly spent. Yeah. Thank you, David. I've got a question here from Gary Keynote. I'm going to read it because it's rather a complicated one to get across, and I won't do that properly. So it is appropriate to use absolute gauging with specific vehicles for assessing new electrification project compliance. That's a question mark. How would this approach be compliant to 2173 and provide compatibility with all 2173 compliant rolling stock?
Yeah, that's an interesting question, Gary. The answer is it's not compatible with it, because 2173 is fundamentally the approach that says we're going to use something that will take any rolling stock going into the future on the basis that rolling stock has to be compliant with 2173. However, the point really is one of, if we have an existing route that has got existing rolling stock in it that is going to be used for the foreseeable future, then it's a question of how we demonstrate that we have compatibility now with that rolling stock. And then any new rolling stock that's introduced, will that be compatible with it in the same way that we have to do physical gauging whenever we introduce new rolling stock? It's not a, shall we say, it's not the best solution in the sense of future proofing, but what it is a solution of how do we get through something now to actually get ourselves with an electrified railway given our current set of rolling stock. So the other side of it, and I have to, beg the question on this one, is there has been assumptions in terms of how pantographs will behave going forward into the future. One of the things that's really bitten us recently in terms of freight vehicle gauging has been that modern freight suspensions are very different to the freight suspensions of yesterday. And the net result of that is that some of the performance characteristics in terms of sway are very different, and therefore we're having to do a significant rethink in terms of what that means to, for example, freight gauges. I can see the same thing possibly happening in terms of pantograph gauges as we move forward to new forms of suspension and look at the innovation that might be introduced in the railway in coming years. So if we are talking about future proofing, we're only talking about future proofing within the context of how long 2173 will still be valid for everything. But beyond that, there would have to be a derogation, for example, to do this. But nevertheless, if we can do that and not get a bridge and not knock a bridge down, I'd say that's actually a good starting point for getting an electrified route, particularly if there's only a few structures on a route that means.
Okay, I'm going to just do two more questions, David, and then we'll move on. We have a question from a colleague in Canada. How is extreme weather, e.g. wind and ice accumulation, considered in the probabilistic gauging methodology?
Sorry, did you say is it considered?
it says how, but is it would be equally good.
Yeah, okay. I mean, in terms of probabilistic methodology, we can certainly look at the wind relatively easily and look at the wind distributions of an area and say we can add that as a distribution into the system that we've got. In terms of ice, I'm not really sure about how we'd manage that, because that's a very, very long-term thing. It's either you've got ice or you haven't got ice. And I suspect that probably what we consider in that situation would be you consider it with ice and you consider it without ice, and you'd weigh up the risks of the two together and make your judgment on it. I mean, I think what we have to look at in terms of probabilistic is there is a whole span of things associated with the application of these tolerances. It's what you include, what you don't include. We did some work fairly recently looking at passenger loading, and we thought there might be some mileage in, for example, looking at the loading of passengers on a train from a point of view of the distribution of the as picked up from mobile phone signals. In actual fact, that's what we used. You know, using a mobile phone signal, you can work out how many people were on a given train. We looked at that for a number of months, and then someone said, well, what happens when you've got a football special that's running through that defines all the rules? So I think what we have to do in all of these things is to make sure that we've got all the scenarios looked at and that we are considering. But that's the engineer in us, and that's actually one of the reasons why we're moving from a, shall we say, a process that's defined by tick boxes and standards that we really don't have to think a great deal about, into one where we're actually having to apply engineering judgment. And really, this is one of the reasons why the Permanent Way Institution is a perfect opportunity to showcase this, because we have engineers here who are interested in the engineering, who can make those judgments and who can look at, should I include ice, should I not include ice, should I include wind, should I not include wind, and those sort of parameters, and make the case for it, and actually put that case together that says, hey guys, we don't have to knock this structure down.
Thank you. Okay, last question comes from Graham Beale for this session, David.
Yep.
Does the use of dynamic or probabilistic gauging include a tacit assumption that the track maintenance regime for ballasted track may have to change?
Well, that's a very interesting one, because in the probabilistic assessment that we've taken through the system, we are making an assumption that the track is, shall we say, capable of being moved from one extreme to the other by the engineer. In other words, we're not looking at track and saying there's a probabilistic movement associated with it. We're actually looking at it and saying Network Rail requires an allowance to move the track up, down, left and right, and we're including that. So we're not actually taking that into account insofar as we're taking the full allowances into account. If we were to take into account the track movements probabilistically, I think we'd probably be gaining ourselves about an extra 10 millimeters laterally, plus or minus 10 millimeters laterally and vertically. But that's a future step. At the moment, it's get it done, given that there are certain constraints in terms of how we manage track at the moment. If we want to change how we manage track in the future, yes, we can certainly accommodate the method. It's a methodology, that's all it is. And we can include in it what we wish to include in it. And if we change our working in the future, our trick now is not to limit ourselves by writing something into it that is going to hold us to it for the next century.
Thank you, David. That, as always, a brilliant exposition of your art form. Thank you.
Thank you.
So we'll thank you, David. If you want to go off,
I'll go away now.
Video. Yep. Yeah. That's it. Go away. That's it. I'll call you back later. I am going to change the way we do the questions at the end of Andrew's talk, which is coming up very shortly. I'm going to call all the presenters back for the final Q&A session and do a bit of a panel questions and answers, if you'll indulge me. Well, David, thank you for your input. It was a real pleasure listening to you, and as always, very enlightening. I am now going to introduce Professor Andrew McNaughton. He is an internationally recognised advisor to governments and railway administrations around the world. Andrew is chair of Network Rail High Speed Limited, which manages HS1. He advises DfT on projects and is chair of the proposed National Electrification Efficiency Panel. He is professional fellow at University of Southampton, an honorary professor at University of Nottingham and strategic advisor to the governments of the Czech Republic and New South Wales. As technical director of HS2, Andrew developed its operational engineering and environmental design and specification, including acting as the principal witness in Parliament. He chaired the World Intercity and High Speed Rail Committee. Previously, Andrew was NR's chief engineer and chaired the EU Rail Research and Infrastructure Committees. His career started in 1973, and that's something of a miracle to have packed that lot in that short a time. Andrew, welcome. It's a joy to see you and a privilege to be able to introduce you to speak to us this afternoon.
Thank you, Peter, and good afternoon to everybody, wherever you are. I wish you hadn't said all that, Peter. You and I go back a long way, and I go back even further with David. And some people confuse, if you're around long enough, you make so many mistakes, people start to call it wisdom. But anyway, let's go. This afternoon, we've heard two national, I would say international, genuine experts in the subject. What you will get from me is a view, I think, very much as a practical business engineer, taking some of that and reflecting upon it. And I've got a couple of reflections before I start, and that's straight out of listening to this afternoon so far. One is, I do welcome the Permanent Way Institution taking this on, because after all, it's about time overhead line and track was seen as part of the same system. They just happen to fit a bit of a train between them. And not just their position, but their behavior depends on the asset stewardship and design of both those disciplines together. It is part of the one system. The second thing really is, it is a system, and the era where one discipline could just go, nothing to do with me, Gov, is not where we're going to be in the future, if they're always going to have a future. Now, we've titled this, and I'm pushing my keys and not getting it to move forward at the moment, which is a bit of a nuisance. We've got control now, I think. You've seen the title. I need to talk a little bit about where we stand in the bigger picture. And Kate, yes. I'm just getting used to the time lag on moving the pictures forward. Sorry about that. We've talked a lot about the engineering system, and particularly about aspects of the overhead line system. I want to bring us back to why we're doing it. And yet Peter has been quite voluble about the climate emergency, and that gives us an opportunity. But let's just get into that a little bit more. This really is slow. We've been through COVID and we're coming out of it. And there's been a lot of doomsday people about what the impact is. Well, it's quite clear. Here, we're no different to the rest of the world. Cities do remain the center of our civilization. They're the center, there's where economic wealth is created and where all social activity is organized. So people are wanting to get to cities. People are wanting to live in cities, but cities behave very differently. London is a bit of a special case. Not only is it the only mega city in Europe, it's a city very, very dependent on so-called white-collar office workers. Over a third of people who work in London work in white-collar industry. Places like Manchester, Birmingham, Leeds are much more typical of cities, not just in this country, but across Europe, which is they have a very substantial office-based workforce, but the majority of people are not office workers. The office workers may well be looking probably are looking to work from home or work flexibly more. Most people, and we need to remember this, most people do not have that choice. Whether they're in manufacturing, it's pretty hard if you're part of a factory to say, I'll work from home. A lot of people are enablers. We are enablers. You can't run a transport industry from home. Doctors are enablers. Teachers are enablers. A vast proportion of our people need to get to work. They cannot choose to work from home. So what does that mean for commuting? The impact we begin to see settling down now. Commuting is probably 3 days a week for office workers, but still at least 5 days a week for pretty much everybody else. But we do face an even bigger challenge in our cost base if we're starting to provide schemes and resources that are only going to be used 2 or 3 days a week. The traditional imbalance of peak becomes worse post-COVID, not better. We got to justify things on the basis of people not being here 5 days a week. And those that do, a proportion of them, and again it's probably a bit overblown, a proportion are looking to use their weekly commuting budget differently. If you only commute a couple of 3 days a week, you can get your head around commuting for longer. The Sunday Times described this as 90 is the new 60. A 90-minute commute is acceptable for 2 or 3 days a week. Is it equally as acceptable as a 1 hour commute was 5 days a week? What do these people really want from their commute? Well, one of the things they want is reliability, and the other thing they want is reasonable cost. Cost and reliability, cost and reliability. Keep bashing away at those two things. If we move to the next slide, and I'm not sure if I'm in control of this, we'll see. What's the impact on business travel? Well, there'll be less of it, but what there is going to be more important. Business travel is recovering very rapidly across Europe. We're a bit behind. We're a funny mob in some respects because people do business with people they meet and talk to and trust face to face. Once they've established relationships, yeah, they can do an awful lot virtually. But a lot of business will always depend, it's a human dynamic, it depends on human contact. If you're going for business somewhere, if you're going to get a contract, if you're going to get employment, your means of travel has got to be reliable. It's no good missing the appointment. Yeah, you might want to get up a bit later, you might want it a bit faster, you might want it a bit more regularly, but fundamentally, it's got to be reliable. If we create an engineering system that is less than reliable, then we're missing the plot. Now, the third form of travel is leisure. Leisure is going to increase because people have more time. Thank you. People are social animals. People will always want to get together. People will want to go to organised sport, organised leisure, organised culture. That is in cities. This is an opportunity for us again. But you don't want to miss the first 30 minutes of the game. You don't want to miss the first act of the opera or the play. You don't want to miss the first course of a dinner. You've got to have reliability. We talk about reliability as if, you know, what is it, 90% of the time, we're sort of roughly getting you there. Well, that's rubbish. You must expect people to expect an utterly reliable system, and that requires it to be properly engineered. But they don't travel even intervally all through the day. We've got, one of the things we're going to have to change is the idea that we're only really there as a passenger railway, and we run lots of funny little passenger trains every hour throughout the day, which is kind of clever use of resource, but you're actually carting fresh air around. We have a huge opportunity if we think about what do we do with the capacity if we're not running underused passenger trains all day. This affects track and electrification engineers big time too, because we're talking here now about freight. And if you will move me to the next slide, please. I'm not talking about diesel hauled heavy freight. That's kind of like so 20th century. I'm talking about the logistics flows into cities. Intermodal. The one thing you will get anybody, I spend a lot of my time, I'm afraid, with politicians, and it's probably rubbed off on me. The one thing you will get people to line up behind is get freight onto rail, get lorries off the road. People want us to succeed. But we can't be an industry that still talks about and freight. You know, passengers, oh, and freight. Freight is a nuisance, it's kind of heavy. We like passenger trains, they're kind of light. We like self-loading freight called passengers. We've got to get a grip here. We're talking about the principal justification for continuing a lot of our railway is going to be freight. Don't design a system that's cute for passenger traffic, but no good for freight. And freight can include all that parcels traffic, palletized freight. Remember, airlines have kept in business in the last 2 years by carting small, high-value freight. We should be doing the same with our so-called passenger railway. Now, what about the opposition? Let's go on to the next slide, please. You read the trite stuff in the press and announcements about decarbonising the road. Don't believe it. One sort of Michael Caine type of, not many people know this, would be how much carbon is there in an electric Jaguar? Well, there is so much carbon in the creation of the battery for a Jaguar SUV, you'd have to run it on totally green electricity for about 160,000 miles before it crossed over in the use of carbon with a petrol equivalent. Don't underestimate just how much carbon goes into a car battery, particularly a socking great big car. If we all drove things like the Google car, the equation's a bit different, but people don't. They go and buy great big electric tractors and sit them on the drive. They are ruining the planet faster than if they bought diesel cars. So just remember, we have an opportunity here if we get it right, if the price is right. The other challenge is pretty hard charging a car if you live on the 14th floor of a block of flats. Leave that to one side. I'm sure there'll be a miracle solution to that. But what does affect us is all the demand for electricity. So even though we as an industry don't use very much electricity, don't think of it as a free good either. There is going to be a huge squeeze on electricity, energy creation, full stop. If you take the government's desire to quadruple the amount of offshore wind electricity generated, allegedly in the next 9 years, quadruple it, that will cost about £200 billion if that was done. And that's not my figures, that's the electricity industry figures. It's not just the creation of all those windmills, and that uses quite a bit of carbon, I'll tell you as well. It's the creation of all the transmission infrastructure. If we get to the point quite quickly where there is not a great amount of electricity knocking around and an awful lot of people wanting it, we are going to be in the queue alongside road transport, mentioned that, alongside heating, domestic heating. If it's a choice between the lights going off and people freezing, us demanding lots of electricity because we're overusing it is not going to go down terribly well. Let's move on to lorries for a moment. Electrifying distribution vehicles like your local parcels carrier is pretty straightforward. They're wonderful things. They trundle around, they go back to a depot, they can recharge at the depot. They're pretty simple. Lorries are less simple. We could say, oh, it doesn't really matter about how we electrify a railway. It doesn't really matter what the cost is. There is no alternative. Well, sorry, guys, there is. And if we move to the next slide. Already funding is creating the first fitment, first practical examples of how to electrify long distance travel without having either sucking great batteries or wondering what on earth to do with lorries. The first is induction charging. You'll see the tests for that happening pretty much shortly. Highways England, I know they've just been changed their name to National Roads, but Highways England has already funded that. The other thing they're funding, if we move on please, the other thing they're funding is overhead line. Overhead line. We should be the blasted experts in this country on overhead line. If we don't get on with electrification, if we say, oh, we'll do it in due course, we'll do it in CP9 or something like that, well, frankly, guys, the opportunity has passed. And this is where I'm really with Andrew Haynes. We need to get on with it now. People will be investing in electric lorries running with pantographs on the M62 in the next few years, unless we can give conviction that we're going to get on and electrify a railway. And if we say every railway we need to electrify needs to be absolutely rebuilt, well, even if cost was no object, we'll be timed out. We cannot do projects which take decades. If we move on, please. So where do we stand? Well, here's a couple of comments. You might not think I was going to start with what does it look like, but I'm going to. And the reason is, I've had the privilege of dealing with 5 different secretaries of state on high speed 2. Some of you know that. When we come to overhead line, yes, we have a discussion about cost, but we quickly get on to it's hideous. And that's why I've used the word hideous. If it's totally over-engineered and over-designed, guys, we can do better than this. We cannot have electrification that is so over-engineered that even the people who want to support us go, shudder, I don't want this. I'd rather we shut the railway and produce a bicycle track, frankly. So moving on, the next challenge is, just remember it wasn't always like this. You can find well-engineered electrification. Yes, of course, I put up a picture of the East Coast, which is Peter Dearman's claim to fame, a Durham viaduct. But electrification doesn't have to be hideous. And when you think where we're going through communities and across valued landscape, engineering is taking what some of the philosophy of this afternoon, which I know has been focused about clearances, and going every aspect of it. How do we make it better? Not how do we make it so clunky that it looks like a child of 5 has designed it, not a qualified engineer. Moving on. Next slide, please. But here's the biggest crunch. Everything costs too much. Why does electrification in this country cost more than double pretty much anywhere in Europe? You know, in those notoriously low-cost economies like Germany, Austria, and Switzerland. Well, you only have to look at some of the things we do. We move on, please, to the next slide, because I'm going to come back to some of the things I've written there. The biggest thing we do before we even think about how we do it is we over-specify it. This afternoon has been about getting rid of over-specifying basic electrical clearances. I hear a lot about things like, oh, we need tens of millimeters in case we want to change the track, in case we don't quite get the track right. Do you think any other country in the world goes, we're going to start knocking down bridges because we can't be asked to get our basic engineering to a high enough quality? This is where poor quality track work, poor quality anything is costing us a vast amount of money. I have a simple approach, and it's an approach I intend to take in this beautifully titled National Electrification Efficiency Panel, which I've been asked to chair as a kind of non-expert. And believe me, in electrification, I'm a non-expert. Now that is, first challenge, I think you heard it from Andrew Haynes. Why should we ever have to reconstruct a bridge? We have a nice picture at the bottom of Stainton, where not only do we not reconstruct it, but thanks to Peter Dearman and a lot of people on Great Western, we also proved that our standards for wire gradients were 50 years out of date. That is good engineering. On the left, I regard as bad engineering, replacing a bridge that we didn't need to replace. Most of our bridges are beautiful. Look at the one on the top right. That is a beautiful bridge, and it's got another century of use in it. We should not be knocking that down because we can't be bothered to engineer it properly. Now, next slide, please. If we get our specification right, there'll be a lot less to do. And that is the best way of saving money. The best way of saving money on an engineering job is to avoid needing to do the work. The next best is what we do need to do it efficiently. Do you think we do our work efficiently in this country? I've got two examples here. One is a sort of, on the left is a kind of job creation world of about 10 people sharing the experience of one person. But what a cack-handed way of doing things. On the right is something which is, to me, even more depressing. It is a highly automated, high-quality system, which is now being turned into a spectator sport. How many people need to stand on a piece of track to share the experience of a piece of high-output track renewal kit? I'm kind of stating it very bluntly because these things matter. Our first job as engineers is to avoid work. Our second job is to do the work that is unavoidable efficiently. Don't leave it to everybody else. This is an engineering challenge. Engineers should do what any fool can do for a quarter of the price. Don't be one of the any fools, please. Next slide, please. We need a philosophy that says we're going to go for high quality, because high quality means we don't need lots of vicarious tolerances. If each discipline of engineering works professionally, then the bottom line is we don't knock the bridge down. If you take that wider, when we do work, don't bespoke it. It's not fascinating to do bespoke operations. Standardization leads to factory production, leads to high-skilled workforce producing high quality. Key word there is standardize. And then if we move to one more slide. We got to get on with this. There will be wires on the M62 by the end of this decade. If we're still predicting it will take us 20 years to wire up our main network. If we're saying there is so much work involved, we haven't got the resources. If we say there's so much cost involved because we've over-engineered it. If we say there's so much cost involved because we're inefficient. We've seen the Railway Industry Association put forward his own analysis. It's a good analysis. I want to push the profession in this country to move that bit further and really engineer electrification as the minimum credible solution at the minimum cost, and not as some sort of fantasy thing. Because you know what? If you were to walk the corridors of the Treasury, the answer is we're not interested. There will be better alternatives. It's called the road. Sorry guys, but that's how it is. Thanks for listening. Peter, back to you.
Andrew, thank you. If you would stay with us, and I'm going to invite David and Richard to join. Whilst they do, Andrew, we have a question in the questions, which I'm going to read to you. It's from Ruth Thomas. She's not putting a question, she's putting a comment. Thank you to you for mentioning the aesthetics, which do actually matter. Currently, we seem to be trying to be even more ugly than the 1960s, spoken as someone who lives near the East-West Rail Works. Now, I kind of have made comments several times in many places about the overhead line structures that we seem bent upon building these days. I wonder if you'd like to just pick Ruth's point up there and just sort of comment on why you think engineers become so risk averse that they have to make an upright structure 12 by 12 instead of 6 by 6.
I don't think we work together properly. You start with, and part of it is people tend to specialize rather a lot. You start with somebody thinking of the worst possible case for the wire pantograph interaction, and then that leads into the worst possible case for the support to that wire, and then another bunch of engineers take that worst possible case and apply, you know, sort of improbable loading. David talked about probabilistic. There's quite, you know, worst possible. It's the same philosophy as David was talking about. If you pile the worst on the worst on the worst on the worst, by the time you get to the foundations of an overhead mast, you need to dig to Australia to hold it up. It's bonkers. Work back to take David's philosophy into everything we do. What is credible? Don't pile worst case on worst case on worst case. And be prepared to understand. If you're an electrification engineer, understand and talk to the structures engineer and find where are the sweet spots that says, if only we could give a bit on that, they can take a huge chunk out of their bit. Work together. It's a system. Even something as simple as a blasted gantry is a system.
Yeah, good. It's a system. You're right. I'm going to drag us back to a couple of questions which have appeared after Richard finished his presentation. Richard, I'm coming back to you with this. I've got a question from both Gary Keener and Tom Kemp. The question is really essentially the same from both of them. What we need to do as an electrification community to help you to get the standards and the documentation and the mandate, if you like, in place from the client organisation, Network Rail, to projects and contractors in a way which fully legitimises the issues we've been talking about. What can we do to help?
Okay, right. Well, the document with all the techniques has been drafted, and hopefully we can discuss it next week at the National Electrification Efficiency Panel. Assuming we get a positive reception there, then we can quickly get it embodied into company standards. We have a process in place to get that into the December update of standards.
Okay.
So, Andrew, we need to make sure that that happens at the.
Yeah. Could I chuck something in? Two things really, but the main one was we talked a certain amount about risk assessment. This is not sort of getting to a place when we adopt all this. It is legitimate. The concern that in each and every location there has to be a kind of 300-page risk assessment is misplaced. One of the things that we need to have, that we will create together, is a set of, if you like, off-the-shelf standard things that says, if it's going to cost that much, this is the, if you like, the risk of absolute bare minimum on everything. Now, how much cost can you avoid on each bridge? You may get the situation where a really, really cheap bridge, although I haven't found one of them in recent times, you go, it is so cheap to reconstruct the bridge, we'll leave everything on desirable clearances, to use an old-fashioned phrase. There aren't many of them, but it's almost the, I'm searching for the words, the ready reckoner risk assessment, rather than working everything from first principles. And designers in the design community, contractors, asset managers can rely on those ready reckoners because we've discussed them up front with the assurers, with the people need to get sign stuff in, give permission, and we've got all our ducks lined up. So we're going to do that.
And I think that's right, Andrew. An observation for me is that there are many aspects of what we build in the rail infrastructure, in the whole system, where we don't go back to that sort of first principles questioning every time we start to do something. How would it be, for example, if we asked for every pandrol clip, is it strong enough to hold the rail down?
Precisely.
We use a production approach that says we risk assessed it many years ago and we just install them. That's where we need to get to with some of this stuff, it seems to me.
I think we're also missing a few tricks along the way, because one of the experiences I had some while ago at the start of Great Western was picking up an assumption that it was better to have very, very stiff supports for the contact system, where in actual fact what you would really like would be to have a contact system that swayed exactly the same amount as the vehicle. Because if you do that, it actually solves a lot of problems. But you know, I'm afraid people would look at the tolerances associated with foundation stiffnesses and tend to pick the wrong ones because they assumed that we were trying to keep it rigid. So there's a lack of understanding somewhere, and it just means you have to go back to basics and say, what are we trying to do?
Thank you, David. And what I was just going to remind us is most of the places I wander around in Europe have fixed track geometry, certainly at critical structures, if not more commonly, but certainly at any critical structures, is not seen as a sort of dreadful imposition. It's seen as just a professional solution.
Yeah, thanks for that reminder, Andrew. David, can I take us on to another question that's come up since you were speaking? This is from Ralph Malang in Melbourne in Australia, who is observing that the probabilistic approaches that you've outlined for gauging have application in other senses. He highlights particularly the apparent vulnerability of the electrification system to wind displacement and hookover dewirement, which doesn't happen. Clearly, there must be some probabilistic approach that one could take to assessing that. Have you ever considered moving your undoubted expertise in that field of probabilistic assessment into other aspects of the infrastructure systems?
Yeah, I mean, absolutely have. I mean, interesting enough that one of the things that I started when I started to get interested in electrification, it was simply because I could see that there were a whole series of issues there that were, shall we say, we were taking into account improbable events. And a big part of the work we did on the original pantograph sway project in terms of defining what the pantograph sways were, we're looking at what events were likely to cause, dewirement hookover type events, those sort of things. So yeah, I mean, the system is very adaptable. Effectively, a probabilistic system fundamentally says all you need to know is how the likely range of the parameters that you're dealing with and the probability of that occurring. And if I say that it usually falls down to something like 75% of all probabilistic of all parameter distributions are normal, 20% are linear, and the remaining 5% is something special. And there's no magic to it in a way. It's just quite simply that, you know, if you're going to toss two coins together, then you just multiply the probability of half together to find out what the probability of them both falling heads up is. It's just applying that. But the trick to it is actually to say, how do we characterize this into the system that we've got? And provided you've modeled the system, which we can model any aspect of the railway now, provided you can model the system, you can put a probabilistic approach into it. The parameters that I tend to use in some assessments I've been doing recently, they've been up to 70 parameters that I've said these are varying all differently in relation to each other. What's the overall effect? It makes a huge difference in terms of, you know, whether something works or doesn't work.
Okay, thank you, David. Thank you. So I've got a couple more questions. I think I'm going to take one off the questions register and then one from me before we close. This one's from Tom Kemp, which I'm going to push in Richard's direction first, if I might. The question goes like this: despite not being recognised in any NR track standard, track maintenance lift allowance is now being written in a route requirement on major electrification schemes. If TMLA is a genuine requirement, should it not be formalised in NR standards? I'm going to ask Richard that question first, and then I'm going to look to my good friend, Mr. McNaughton, whose track expertise is second to none, perhaps to give us a view on that. So Richard, do you want to go first? Richard, I think you're muted.
Yeah, I'm not a sound engineer or a track engineer, but yeah, I agree. If track maintenance allowance is a requirement, it needs to be in a standard, and at the moment it's not in any network standard.
Thank you. Andrew. You're muted as well, Andrew.
I fear being slightly provocative here.
Go on.
Am I?
Yeah, you're on. Yeah, we can hear you. Yeah.
No, I didn't think I was. I'm going to be the risk here by asking me, Peter, is I get slightly provocative, which is the reason you asked me.
I wouldn't have put the question to you unless I wanted you to. Go on.
Right. I think it goes like this. I talked about the cost of poor quality. It is perfectly possible with either with skilled people or with technology to put the track in the right position. Generally speaking, we pay someone to put the track in the right position. If they won't put it in the right position, we shouldn't pay them. This is an approach you see elsewhere. You wouldn't accept it if someone put the roof slightly askew on your house. You wouldn't be very happy about it. Just because you're using taxpayers' money doesn't mean it's acceptable to accept poor quality. In terms of track lift, I don't know why we're lifting track. I really don't. I regard track maintenance as restoring track to its right position. Not if you've got to lift it out of some quagmire, it's because you haven't done the foundation right. I don't see the need to lift track. I see the need to restore track periodically to the correct geometry. It should not need lifting more than a few millimeters, at which point it settles back. That's all.
Thank you.
Oh, no, there is something. If you want to have the privilege of lifting it 3 or 4 inches in old money, you pay for it. You can come out of your budget to replace the bridge because it's not necessary. It's your privilege to specify it, come along with the checkbook and pay for it. You can have the bridge. But don't expect somebody else to pay for the bridge because you won't engineer it to the right standard. That's all.
And I think that last message is the correct one, and plays back to David's point that how do we get ourselves psychologically to build electrification and not rebuild the railway whilst doing it. I think I'm going to close the questions session by asking one that I'm going to put to all 3 of you, really. I'm going to start, the question's quite simple. In the context of what we've been talking about, do you actually believe that we can avoid rebuilding more than 90% of the bridges that exist on the infrastructure today? In other words, that electrification, as we roll out TDNS, will not have to deal with more than 10% of the bridge population. Do you really believe that, Richard?
I believe it's even more so than that. I think we can get those numbers down from 10% down to 5, or maybe even less than that. From all the work we've done, every bridge we looked at, we can have a solution that doesn't involve rebuilding the bridge, and as a worst case, a very small track lower.
Thank you. David?
I believe we can. The question of whether we will, I believe, relates to how efficiently we actually monitor what's going on and how we actually police the spend of money. I believe that we've always been in a situation where the pot of money has been looked at as being the godsend to rebuild the railway as opposed to do the job in hand. And I think that if we actually start to look at the specification of what we want to achieve, which is either we're going to electrify or we're going to electrify and allow, for example, 9'6" containers to go through. Note, I'm not saying W12, I'm saying 9'6" boxes are the future at the moment as we see it. W12 with tank tops and all sorts of things like that is not the future as we necessarily see it. But provided we specify exactly what we want and that we can police that, and I'm glad to hear that there's some 4-letter acronym being set up that's going to police it, if that's what it is. What is it? NEEP? Remember NEEP? It sounds very Scottish to me. That's going to actually police this stuff, and it's going to have someone who's actually looking at it and ask the question as to why are we doing this. If that was tasked with saying we're going to achieve this figure of no more than 5% rebuilds, I'm absolutely certain that that would make people think a lot more carefully about doing it. And yes, I genuinely believe it's possible, physically possible. It's only a mindset that's going to stop it happening.
Thank you. Andrew, as the neats and tatties general in chief.
Don't overplay my role, which is marginal in this. I'm completely with Richard and David. It is not only is it possible, it's inevitable. It's inevitable. It's possible because actually I keep meeting almost everybody I meet. Now I'll say just about everybody I meet, of whichever engineering discipline, understands they can do it, but for some reason in the last 15 years or so, believe they haven't got permission to do it. Our job is not, we don't need better engineers. You're good engineers already. Maybe our job is just to give you permission to be good engineers. And the other reason I think it's inevitable is, well, it's inevitable that electrification will be done without reconstructing bridges. Or I'll put it more starkly, if we believe we've got to reconstruct all the bridges, there won't be electrification.
Yep.
There is not a limitless checkbook. The old Network Rail credit card has been cut up in two. This is the time when we really show what good British engineering is, guys.
On that rallying cry, which I think is a really important rallying cry to everybody listening today, I'm going to draw the panel session to a close. And before I go any further, I'm going to sincerely thank the three presenters this afternoon for the excellent job they've done in giving us their views and helping us through what is probably at this stage the most important issue for us in the electrification community to tackle. To Richard, David and Andrew, you can't have a round of applause on this system, but you can have mine. Thank you very much, gentlemen. Can I invite you to shut your video off and your sound off while I just make a few closing remarks? I hope everyone who joined, and there were a substantial number of people on the call, it was 250 plus for a long time. Some have had to start dropping off, I see. I hope you found this afternoon beneficial and interesting. I hope also that you will take some of those core messages to heart and take those away and live by them, really. I would like to thank you for joining in, and if you have been all the way through, thank you for listening. The recorded conference and the materials will be available on the PWI website soon. You will also receive a feedback survey. I wonder if I could impose upon you, please, to complete that survey, because your feedback genuinely is used to help us sharpen our approach to managing these events. I'd like to take another chance to just plug the membership of PWI to all of you interested in electrification. PWI offers us a superb opportunity to create the electrification professional community that we haven't over the years been able to manage through the other institutions. Please consider joining the PWI if you haven't already done so, and give a thought to the diploma education courses for you and those around you, and please explore that. I'd like to just say thank you to Kate, the PWI's Director of Operations, whose meticulous efforts have made this conference happen and run smoothly. I think it's run smoothly this afternoon. Thank you, Kate. That was your round of applause as well. And one final point, the main conference will occur on the 21st of April in Glasgow next year, face-to-face in a room where we can debate much more than the scope of this afternoon's discussion. And I look forward to seeing many of you in Glasgow. Please come along if you feel half inclined to do so. With that, I am going to wish you goodbye and wish that you stay safe. Thank you for attending.